My name is Terrence Mora. I'm a PhD candidate at the University of Delaware. I'm in my fourth year. I'll be attending the meeting this year, so you can come find me and hang out. But today I'm going to be helping you guys with what not to do in a Pitch 120 kind of situation. So I'm going to present a talk where there's too much jargon. And this is kind of rolling off the good talk that you're going to see from Heather Manching, who's also a graduate student here. So it's going to be the same kind of talk, but one with too much jargon. So, right, it goes. So, all right. The global population is anticipated to rise by 12.5 billion people within the next 50 years, which is an increase of at least 50% from what we have now. But to increase this growing population, what we need to do is to improve and increase the production of our staple crops. One of the staple crops that we have, a major staple crop, is Zea maize, and Zea maize provides 20% of the caloric intake for the population, for the global population. And so in order to improve and increase the production of this crop, maize, what we need to do is to be able to unravel the genetic diversity of this crop. And in order to do that, there are many tools which are available to us, such as populations, structured populations, such as the Nilus population, such as magic populations, which are out there. We also have linkage maps which have been made in the past. With the advent of NGS, we're now able to improve upon these tools that we currently have and be able to get more inference into some of the traits that are underlying some of the features that we see in these populations, in the individuals in these populations. And with NGS coming to the fore, we're now able to use RRS methods such as GBS, and these allow us to be able to dissect the architecture of these populations and to get better population inferences. And once we do that, we'll be able to start helping breeders to produce better crops which can be grown in arid conditions, flood-prone, disease-prone regions where production is not possible right now, but we will need to use these regions as time progresses. So that's my research. Thank you.
I focus on feeding 12.5 billion people, not because that's how many people we have in the world today, but that's how many mouths we're going to need to feed in the next 50 years. We need to strengthen the crops that we grow so that they can evolve and adapt to changing environments while still producing enough food to feed our growing populations. In order to do this, we need to increase the genetic diversity of corn grown in the US, which contributes to 20% of what's eaten worldwide. What is genetic diversity? Think of it as a toolbox. Let's say you want to take a tree, turn it into a table, but all you have in your toolbox is a single screwdriver. Sounds pretty complicated, right? Well, now imagine you have a chainsaw to cut that tree down, a drill to screw the pieces together. The corn grown in the US today is equivalent to having a toolbox that only has a single screwdriver. We need to stock our toolbox with the tools required so that our crops are drought tolerant, disease resistant, and can produce enough food to meet growing demands. However, in science, it's not as easy as going to the hardware store and buying a few extra tools. There are certain barriers that we need to overcome. What my research focuses on are what these barriers are, how we can overcome them quickly to increase the genetic diversity of corn and feed those 12.5 billion people. Thank you.
Hello, my name is Dominic Kate, and I'm a PhD candidate here at The Ohio State University. What you're about to watch is a rendition of what my Pitch 120 looked like when I was a first-year graduate student speaking to a non-plant pathology audience.
Hi everybody, today I'd like to take a moment to talk about something you probably don't think about that often, and that's the importance of the global rice crop. Rice is one of the most important crops on the planet, and not just economically. It has its value rooted in our culture, and is even being looked into as a source for fuel. But what's really important about rice is our reliance on it as a food source. It's been said that 23% of all calories consumed by humans are done so in the form of rice. So, With our increasing global population, it follows that we also have to increase our rice yields. However, there's a caveat, and that is that our productive farmland doesn't increase with our increasing population. So we have to think of more creative ways in order to increase our rice yield rather than just planting more rice. As a society, we have 4 categories that we use to rank challenges in crop production. And in 3 of these 4 categories, rice blast disease caused by the filamentous fungus Magnaportho oryzae is in the top 3. And in the 4th category, it ranks number 6. This disease accounts for 10 to 30% of annual rice yield loss in 85 countries, which is a numeric way of saying everywhere rice is grown. These losses are estimated to be enough to feed 60 million people. So what can we do about it? Some are trying to make the growing conditions more favorable for the rice and conducive for the fungus. And that is mildly effective, but is proving costly and therefore impractical for the rice growers in developing economies who make up the majority of the growers. Resistance genes have been identified and bred into the planted rice cultivars, but it's only a matter of time before the fungus evolves in order to evade these resistances, and there's many places where these genes do nothing in order to prevent the disease. For every one of these resistance genes, there's a cognate avirulence gene in the fungus, but we're practically in the dark when it comes to their identity and their functions because of their obscure sequence patterns. The goal of my project is to identify the cognate avirulence gene to the PI2 resistance gene in rice in order to shed some light on this strong relationship. This way, the more we know about our avirulence genes, the better prepared we can be in order to select longer lasting resistance genes and take a step forward to solving world hunger. Thank you.
If you're interested in finding out how this project has progressed over my tenure at OSU, I do have a poster at this year's annual meeting in San Antonio. Thanks for watching, and I look forward to seeing you around the meeting.